Section 7-3, Part 3. You can use linear functions to analyze situations, make predictions, or draw conclusions. We're going to look at an example of using rate of change of linear functions. When a scuba diver goes underwater, the weight of the water puts pressure on the diver. The table shows how the water pressure on the diver increases as the diver's depth increases. A part. What is the rate of change of this linear function? That should be an N. What is the rate of change of this linear function? What does this rate of change represent in this situation? Well, the first thing we need to do to find the rate of change is to determine the change of the inputs and the change of the outputs. So let's begin looking at this table. What is the change from 10 to 20? I see that it's increasing. I must add. 10 plus what number will give me 20? Well, that's 10 plus 10. Well, let's try 10 again. Is 20 plus 10 30? Yes. Try again. Is 30 plus 10 40? So I do see, yes it is, I do see that my inputs are the same. They're constant. All right? Now let's try our outputs. 4.4 plus what number is going to give me 8.8? If you need to, punch those in your calculator. Take the larger one, 8.8 minus 4.4. You see that you should get 4.4. Now, let's try 4.4 again. What's 8.8 plus 4.4? Punch it in your calculator. What is 8.8 plus 4.4? Well, if you add those together, you get 13.2. So yes, I still am adding 4.4. Continue on, adding another 4.4. Is 13.2 plus 4.4, does that give me 17.6? And yes, it does. So I do see that I have a constant rate of change for my input and a constant rate of change for my output. So therefore, the rate of change, remember, it's change of output, which my change of my output is 4.4, divided by change of input. My change of input was 10. So change of output was 4.4 over change of input, okay? So this would mean, let me tell you what this means. This means that the water pressure increases 4.4 pounds per square inch of pressure for each increase of 10 feet in depth. So this means that the water pressure increases 4.4 pounds per inch, per square inch, 4.4 pounds per square inch of pressure for each increase of 10 feet in depth. So you can go back and see the diver's depth is in feet. The water pressure is pounds per square inch. So your rate of change is 4.4 over 10. Next, it also says on our B part, use the rate of change to predict the water pressure of a diver at a depth of 60 feet and at a depth of 100 feet. So you notice our table only went to 40 feet. So we're going to use this same rate of change to predict the water pressure of a diver at a depth of 60 and then again at 100 feet. So I've kind of drawn a table for us here. Now we want to go on down to 60, so I'm going to go 50 and 60. This was what I need, that point. And then I also need to go on down to 100. So I'm going by tens. So that's 70, 80, 90, and then I have 100. So this will be an answer as well. So we're going to need to extend our graph. Now remember, our change of our input was 10 each time, and that's what I've done each time. I've added 10, as you can see. I went all the way down to 100, okay? Now remember that your change of output was 4.4. So each time we added 4.4. So if we continue adding 4.4, 17.6 plus 4.4 gives me 22.0. If I add 4.4 again, I get 26.4. You can use your calculator. Take 26.4 and add 4.4 again. You get 30.8. 30.8 plus 4.4 with your calculator, you get 35.2. Add 4.4 again to 35.2. You end up with 39.6. And add 4.4 again, and you get 44.0. So once you know that your rate of change is constant, you can make predictions, you can analyze situations, and you can draw conclusions. So by extending this table, the water pressure at 60, that was one of the questions, the water pressure at 60. So the water pressure at 60 feet is 26.4 pounds per square inch. Okay? All right, so we were asked about 60, and then we were asked about 100. So here we are at the 100. We go to this point. We found 60, it was 26.4. Now we go to 100. So the water pressure at 100 feet is 44 pounds per square inch. So there's your two answers, the one for 60 feet and 100 feet.